Okay, so let us start this morning with the two last lectures by Valentina on many-body localizations. Please.
Yes, thank you. So before starting, I promised some references on logarithmic light cone, which was part of the discussion of yesterday. So this is, I would say, the first paper where they proposed this, and they derive, so under the assumption that the Hamiltonian, the many-body Hamiltonian has this structure that I referred to as an effective model. Yesterday, they derived this modified version of Lieb-Robinson bound, which has a log of t instead of t. And then this is numerics, which is done, in this case, for entanglement entropy after a local quantity, in this case with local operators. So if you want to, I think these are the first papers looking at this numerically, so if you want to have a look at them, those are the references. Okay, now let me restart from where I stopped. So I was discussing, I ended by discussing these ideas of conserved quantities in MBL. So this is a recap of what I said very fast towards the end yesterday. So let me consider in general this Hamiltonian, which is now the full interacting Hamiltonian. And as you see, I am rewriting this in a basis which is no longer the position basis, but it is the basis of single particle states, which I label by alpha. And in this case, the interaction term becomes, in general, 4 fermion terms, where, again, alpha, beta, gamma, and delta are these indices of single particle states. And then I was mentioning that if you switch off the interactions, so you just have your Anderson model, you know what are your quasi-local conserved quantities in that case. So they will just be the numbers of these single particle states. And the reason why they have this quasi-local structure in the norm is inherited from this peculiar exponential decay structure of the wave function of your Anderson Hamiltonian. If you expand your operator n alpha in the basis of position for your fermions, the coefficients in this expansion are just products on the sites I and j of your single particle wave function. And then you know that the wave function has this structure in here, so it decays away from this region around the localization center. And therefore, you can deduce that in this expansion, these amplitudes are themselves exponentially decay in the distance between the particular region in space where your wave function alpha is localized, so let's say the localization center that I call R alpha, and the support of the particular operator that you're looking at in this expansion, which in this case is just the collection of the sites where fermionic operators act, so the sites I and j. So if I take operators which act far away from the localization center, I have that the amplitude of my occupation number is exponentially decaying. And therefore, the norm of this operator is exponentially decaying in my lattice. And now the idea is that something similar holds true also if you switch on this, this interaction term. And the intuition is very similar to the one of Fermi quasi-particles or Landau construction of quasi-particles in Fermi liquid. And it is that when you have interactions which are non-zero, but let's say small, so let me write it like this. And you want to build conserved quantities, which now are conserved quantities for the full many-body Hamiltonian, which I called I alpha before, then what you would expect is that these quantities are some weak deformation of these occupation numbers in the non-interacting case. And the way you can implement this, this idea, this intuition, is by writing down an operator expansion around your occupation numbers, which now will have a form which is more complicated than this. So here, without interaction, you have a quadratic Hamiltonian, so everything in your expansion will be quadratic as well in your fermions. Whereas in this case, this is no longer true, so what you have to do is to dress this non-interacting occupation by arbitrarily long strings of creation and occupation and annihilation of fermions. So let me write it down. So you will have, in general, a sum overall n, and then what you have to do is you sum over index sets which I call I and j, of length n. Okay. An amplitude for the corresponding operator alpha labeled by these index sets I and j, and then you have some operator ij, and then you also add the complex conjugate. So what are these index sets? Well, these are just collections of indices of single particle states. So let's say that here I have alpha 1 up to alpha n, and for j I have beta 1 up to beta n. And the operator O is now, Oij, is now a product of CDAG alpha 1, CDAG alpha 2, and so on and so forth. So this will be a product for k which goes from 1 to n of CDAG alpha k. And then I have the distraction operator. So let me call it k prime of C beta k prime. Okay? And you're summing overall possible lengths of these operators. And the claim is that when you are MBL, you can make such a construction, and these coefficients conserve this property of being exponentially decaying. In this case, what you have to do is, so you have the support of your operators will be made by many sites in principle, so you can approximate the support for each of these CDAGA, for example, with the site which corresponds to the localization center of the corresponding single particle wave function. And then what you have to do is to show that you have a decay with respect to the maximal distance between all of this localization center, which contribute in the particular term in the expansion that you're looking at. Okay, so how do you do this? So this is the motivation for what I'm going to do in the following. So how do you fix these amplitudes? Well, you have to impose that this operator is conserved, so you will have to impose a commutation relation with your many-body Hamiltonian. And then if you re-express this commutation relation in terms of these amplitudes, you will find that you have some sort of linear equations between these amplitudes that look very similar to some Schrödinger equations. So you can interpret this amplitude as the amplitude of an effective wave function for an effective single particle problem. So the wave function is labeled by alpha, and I and j is some site on a lattice that we call an operator lattice, where you're looking what is the amplitude of the wave function. And the structure of the lattice is encoded into this equation, and it will be determined by interaction. So this is just to give an idea that when you try to work out this construction, you can essentially map this into an effective single particle problem, which is more complicated than an Anderson Hamiltonian, because you have correlations between the on-site energies in your lattice, and you have to work out what is the particular structure of your lattice and how it depends on these interactions. But then if you are able to do this, and if you're able to prove that this effective single particle problem is localized, then you have for free the fact that this expansion converges in norm, and it converges to some quasi-local operator. So I'm not going to discuss this problem, but what I'm going to do is to show how you somehow argue for this exponential localization in the Anderson model itself, which is a little bit simpler. And then from there, you have to generalize it to this more complicated case. But conceptually, I would say that this is quite straightforward. Okay, so I hope this motivation was clear. And then let me go to this part 2. Where I will go back to the Anderson model and to the estimate of the transition point for single particle localization. And there are two parts in here, so let me start with the first one, which has to do with redefining what is my criterion for localization. And you will see that this, so I will introduce an order parameter for this dynamical transition, which is a functional order parameter, which is actually a probability distribution. Okay, so for this, let me introduce some notation. So I rewrite my Anderson and Milton now in first quantization because it's more practical. So I have a sum over all sites on my lattice of my random local potential times the projection on the given site A. And then I have the hopping. So just for clarity now, I put a dependence of the hopping on the particular sites that I'm looking at, and then I will put all of them equal to V, but this helps to keep track of the diagrammatic. And then I have this operator here. Okay. So this is what I will call H0. And of course, this is an Hamiltonian which is trivially localized. And this is my hopping that I will call V and that I want to consider as a perturbation. So I will set up a perturbative expansion in this hopping term in here, a little bit like in the non-resonant two-side case that we saw yesterday. Okay, then the eigenfunctions of these, I call them E alpha. Okay. And I think about the very first picture that I showed you regarding these experiments of condensates and the trap being released. So what I want to do is some sort of quench again. So I start, this is my lattice, and I want to start with a wave function which is localized in one specific site. Let me call it A. So my psi of 0 is just the eigenstate of position operator at the site A. And then I time evolve it with this Hamiltonian, and I look, for example, at the survival probability, which tells me what is the amplitude to find my degree of freedom at the very same site where it was at time t equal to 0, at later time in my evolution. So let me introduce this survival probability as, well, I take positive times, and then I have just the projection of the time-evolved state. So now my full Hamiltonian, I drop this notation here. I just call it H. So this is the time-evolved state, and then I project it back to the original site. Okay. And now this probability, I can express it in terms of, so I want to just introduce green functions and self-energies. So this object here, let me write it, let's say, as a anti-Fourier transform of its Fourier transform, if you want. So this will be given by the limit. So again, I have this infinitesimal dissipation that I have to add to regulate or to make my integrals converge. And then I integrate now over an energy e to the minus I et. And here I put a local green function evaluated right above the real line in my complex plane. Okay, so what is GA of Z? So this is the diagonal matrix element of the resolvent operator. Okay. Which is an analytic function, at least if I take if I am away from the real axis, this is analytic, and of course, it has singularities at those real values of energies which belong to the spectrum of the Hamiltonian that I'm looking at. Now this quantity, so this is in principle GAA. Let me rewrite it to introduce a local self-energy. So this I can write as Z minus the local energy in absence of my hopping. So when my Hamiltonian is just equal to H0. And then I have a shift, which is generated by the fact that I'm adding this hopping term, which I call S, and which depends on the particular site that I'm looking at. So this is a local self-energy. Which is 0 when V is equal to 0, and it is in general of order V squared, where V is the typical size of my couplings VAB. Okay. And now, because my function is analytic, what I can also show is that, so these are things which I'm just recalling to introduce notation. So this, I can give an integral representation to this, which, where I just have to insert, let's say, the spectrum of my Hamiltonian. So I can rewrite this as the integral without 2 pi, okay, of a spectral measure, and then I have Z minus, and I can replace my Hamiltonian with the particular value of E that I'm integrating on. And this object in here is nothing but the local density of states. Which for a finite system, okay, is obtained as summing over all the eigenstates of your Hamiltonian. The weight of the corresponding eigenfunction on the particular site that I'm looking at, so this is why this is local. And then I have the condition that I'm looking at an energy where I indeed have, which belongs to the spectrum of the Hamiltonian. Okay, so last thing regarding notation is that, so I can write down this representation for my resolvent, but I can also do it, or for my local green function, but I can also do it for my local self-energy, which has the same analytic properties of the green function. I will have to introduce a modified measure, so you can work out how to get this measure in terms of eigenstates of a perturbed Hamiltonian, where what you have to do is, if you're looking at the self-energy at a particular site A, you have to eliminate, let's say from your lattice, all the links which connect the site A with the other sites, and then you compute the eigenfunctions of what remains, and you can express the measure which enters in the representation of the self-energy in terms of those new eigenfunctions. But for the moment, I will just, so we can comment on this in the discussion, but let me just write down the formula here. And let me just call it gamma. Okay. Okay, so these are the objects which we need in the following. And now I will tell you how to deduce the behavior of this survival probability in terms of these quantities that I just introduced. So I will state 3, let's say, facts. So the first one is that the behavior in time, in particular at short times of this probability, depend on what is the analytic structure of these measures in here, so the local density of state and the analogous measure which appears in your self-energy. And this is something, so I will write it down and then I will comment. So in particular, it depends on the type of singularities of these measures that you have on the real axis, so in your complex plane, so this is gamma. And what you have to distinguish between is whether these measures are, as mathematician says, pure point measures or absolutely continuous. So pure point simply means that you can think at these measures as being a collection, accountable collections of delta functions, as you have in here, which is typically true whenever you have a finite system, because you have discrete eigenfunctions and discrete eigenvalues, and therefore your density of state is just a sum of delta functions. Whereas absolutely continuous is a measure continuous. Sorry. Is essentially a measure which is associated to a density. So you can think of this as being of the form of some density times dE. So it's the continuous version of the sum of delta functions. Okay, so why does this matter? So let me take this example of having a finite system. So the volume of my lattice is finite. And then I know that indeed I have my spectra decomposition. And I know that, for example, my eigenstates are properly defined eigenstates, so they are normalizable. In general, they belong to the space of square summable functions in my lattice. Okay. And whenever this is the case, then I can easily show that this function, a little bit like when we discussed dephasing, so in this case, is actually simply a quasi-periodic function, so it's a sum over a finite number of frequencies. Which gives me something that kind of oscillates. And I will just compute it in a very pedantic way, just to make one point. So let me recompute it. So of course you can directly, so this was a matrix element of e to the minus ith, so you can directly plug a resolution of the identity and you would get immediately that this is a sum over frequencies of e to the minus it times E alpha, where E alpha is one of the eigenvalues of your Hamiltonian. But let me, let's say, get this expression by using this formula up there, just to stress something. So this tells me that this is my measure, and then I have this, and then I have the green function, which now I expand in the basis of eigenfunctions. So I have my local weight and the energy denominator. So this is E prime plus I eta minus E alpha. So this is just my local green function computed at E prime plus I eta. And now the way I can do this integral is just simply, so you see I have simple poles in here, so I can use the residue theorem. And I see that before taking the limit eta going to 0, I have an expression which is, so I have still this sum over eigenfunctions. This, and then I have terms which contribute at the exponential, so there is the term which I expect, so these phases, and then there is this infinitesimal dissipation that gives me this suppression term, e to the minus eta t. Okay, so the idea is that this is what I would like to interpret and to call a decay rate. So it tells me what is the rate of decay of my excitation which I created at the site A. And you see from this very simple calculation that this decay rate is, in some sense, related to the imaginary part of the poles of the expression that I am integrating over. And of course, in this case of a finite system, this imaginary part is just eta, so when I send eta to 0, this disappears and I have no decay rate. And I'm left with this quasi-periodic function. And based on what we said yesterday, what we expect is that if we instead have delocalization, which requires at a certain point to go to some infinite volume limit, then what we expect from our system is that we add this, this infinitesimal decay rate, and the system self-sustains such a decay, and eventually I am left, even when I take eta going to 0, I am left with a decay rate which is finite and which is of order 1, and this is what would correspond to delocalization. And this is what happens in general for systems when I go to the infinite volume limit. So in general, if I take my volume to infinity, what I find is that my survival probability will have, well, there will be some coefficient that may depend slowly on time, and then I have a finite decay rate, which dominates at least at short times, and then I could have some other term which corresponds to algebraic decay, which is important if I look at the dynamics at later times. But this is finite, and whenever this is finite, I talk about delocalization. So I create an excitation here, and this decays in the rest of the lattice, and I lose it from the particular site where I put it at time 0. Okay, at this point, one may be confused because I say that having a finite decay rate is possible only whenever you have an imaginary part of your poles in an expansion like this. But then, of course, your Hamiltonian is unitary, so how can you have imaginary parts of your poles which emerge in your system when you know that the spectrum is completely real? And this is related to, so I think this was already discussed last week, so it is related to this idea of having a spectrum which becomes continuous in the thermodynamic limit, which at the level of singularity means that if you look at your green functions or at your self-energies in the complex plane, so in a finite lattice you have poles, which are in general simple poles because you have no degeneracies if your system is random. And then when you go to the thermodynamic limit, these poles kind of condensate and they give rise to a branch cut along the spectrum of your Hamiltonian. So when you have a branch cut, then, so what I want to do to compute this survival probability is essentially to compute an integral which is right above the cut. But to do that, I usually want to do some rotation in the complex plane, which means that I want to analytically continue my green function, which in principle is well defined away from the real axis, so for imaginary part of z positive. I want to continue it to the lower half of the complex plane. And I have to pay attention because, of course, there is a branch cut, so there are, the continuation depends on the path which I choose. So I will have, in general, different Riemann sheets, and I have to pay attention on which one I am when I do my continuation. So just to give an idea, if I start from here, and here everything is well defined, and I analytically continue around the cut, so I am in the same sheet. So this, you have to imagine that this is really, okay, so I cannot draw this, but if you go to the supplementary file, there are drawings which I took from the internet, which are much better than whatever I may be able to do in here. But the idea is that if you do this, if you follow this path, you are in the same sheet, and you find that if you compute the green function in here and the green function in here, there is a discontinuity, which is imaginary, up above and below the cut. But then what you can do is you start from here and you go across the cut to the second Riemann sheet, and then your function is continuous. So what is my function then in the second surface, or sheet of the surface? Couldn't hear you. Yes, so that's why you have to, in general. Okay, so this, I will find that this goes like this. So it is as before, where now by this, I mean the integral representation that I introduced before, now computed at z, which has a negative imaginary part. But then I have an extra term in here, which is purely imaginary, and which is related. So I'm sorry that this is squeezed. But this is precisely the imaginary part of my self-energy. So it is this measure here that I introduced in my integral representation. So when you try to compute this integral for the survival probability, and you do this rotation, which forces you to go to the second of these sheets, there you will find that you have developed a non-zero imaginary part, and so you can have poles in there which contribute to the decay rate which you see in here. So I hope this was a bit clear without drawings, but if not, I think the drawings help. So I invite you to look at them. Okay. Maybe this. And this is, by the way, this is the amplitude of the discontinuity, or is half of the discontinuity that you have if you do this path instead of going across the cut. Okay, so, but then you have this that enters in your integral, and as I say, this can have poles. So a pole z star will satisfy this relation. And what you do is try to understand how this pole looks like perturbatively, for example, in V, which was my potential, which I erased. So you can set, just to have an idea, this Z star will have a real part and an imaginary part, which is negative, but let me put a plus. And if you plug this into here and you do an expansion in your potential, you find, for example, that to linear order, you can write this gamma as the imaginary part of your self-energy evaluated at the unperturbed energy, which is of order v square, and then you have higher order corrections. And if you think a little bit, you would recognize that this is essentially what Fermi-Golden rules give you in this particular system. But you can somehow go beyond and compute higher order corrections. The only thing that I wanted to stress is that somehow this gamma here is related to the imaginary part of this local self-energy that I just introduced. And so this is the quantity that I want to track when I want to prove that I do have delocalization or not. So the relevant quantity will be this function gamma E, which is minus the imaginary part of my local self-energy, of course, in the limit. Okay, so this is E plus I eta, in the limit when eta goes to 0. Okay, so this is the central object that we will try to compute. And now let me tell you two more things. So the fact number one was that I have a finite decay rate when, in this limit, this imaginary part is non-zero. The fact number two is that, in general, this does not. This happens in infinite volume systems. So in general, you do delocalize, and you have a decay rate which is finite. But there are infinite volume systems for which this does not happen. And one example is so no decay rate. So one example which you can think of, which is trivial if you want, is that in which my potential is equal to 0. And so in that case, your Hamiltonian is just purely local. These can be random variables. But I know that really the spectrum is made of a countable set of numbers, which are these numbers in here. And I know that the eigenfunctions are still belonging to my Hilbert space. They are just the local, the eigenstate of position operator, and they are, of course, square summable, even in my infinite lattice. So this is a special case, but of course, it's to say that it is not always true that you have a finite decay rate, obviously. And the second example is localization, which is a case in which V is non-zero, but still you preserve this property of being well-defined eigenstates, which are normalizable because they have this exponentially decaying structure, and of having a spectrum that has this pure point nature, and this is what in math is usually referred to as spectral localization, as opposed to dynamical localization, which is what I said the first day, namely the fact that you look at the conductivity and you show that this is exactly equal to 0. Okay, so this is V equal to 0, and this can be also for V different to 0 if you are localized. Okay. And now the last comment on this is that so far I reasoned in terms of having a random potential which is given, which is fixed. But the argument, as you see, relies on understanding some fine structure of my measure and analytical properties of my measure. And to do this, when I have a random potential, I have to be careful on the way in which I average over this random potential. So let's now take this random, and in particular, this will imply that my eigenvalues in a finite system are also random. And I care about the structure of the local density of state or the imaginary part of the self-energy, which is a measure itself. But let's think about the local density of state. So I want to distinguish whether in the thermodynamic limit this is a collection of delta peak or it smoothens and it becomes a continuous function. But if I average this object directly over the disorder, I wash out this information, this distinction. And the reason is that if this is pure point, so it is a collection of delta, the location where I have my delta peaks, they will become, of course, they will accumulate when I go to the infinite volume, but let me draw them like this. But the location where I have my eigenvalues is random. And once I average over all possible realizations, I recover a density of state which is smooth. So this object in here, where now I'm averaging over the epsilon here, doesn't know about whether I have a localization-delocalization transition. This is smooth at the transition. It's a bit like the partition function in the MBL case. So it is not enough to look at its average over disorder. What I have to look at is actually the full distribution of this object over my disorder realizations. So this means that the correct order parameter for this dynamical transition would be the following. So I have to take these usual two limits, and then I have to look at the probability distribution of the imaginary or minus the imaginary part of the self-energy at E plus I eta. And I ask, what is the probability that this is positive? And in this limit, I can have two outcomes. So if the probability that this is positive is itself different from 0, then I am delocalized. And if this is 0, I can say that localization occurs. So if you want to interpret this in the language of usual phase transition, indeed, the order parameter that you have to think about is a full probability distribution in this peculiar order of limits. So in particular, what happens when you are localized is that at finite eta, so if you are localized and you look at this distribution at finite eta, so this, remember that I called it gamma, you look at the distribution of this gamma over disorder, and you will find, in general, something like this. So this is gamma, and this is P of gamma for eta finite. In the localized phase, you find that this peaks sharply around values which are of the order of eta. And then it decays with a tail that is that actually you can compute. It has an exponent which is, I think, 3/2. And then you have a cutoff at 1 over eta. So you can compute distribution at finite eta, and then you see that when you have such an object and you take the limit eta going to 0, this squeezes and diverges at the origin, and you converge to a delta function. At 0. Okay. Yes? No, you are localized because you want this to be 0. This is your decay rate. So in some sense, if you are localized, you're not breaking symmetry, and if you are delocalized, you are breaking your symmetry, which is time reversal once more. Okay, so now computing this looks a bit complicated, so now I want to tell you what is the approach that was set up by Anderson in his paper, which essentially corresponds to writing down a perturbative expansion for this object, and then controlling, so you cannot average term by this perturbation theory, as we did last week in the course of SACHDEV. You have to somehow follow what is the probability distribution term by term of this perturbative expansion, but under some approximation, you can do this, and this approximation will give you an estimate of how strong should the disorder be to be in the localized phase. So I don't know, maybe we can take a break here because it's a bit early, but it's okay.
Any questions before the break? Okay, then. So we reconvene at 11. 11 is fine.
Okay.
Please take your seat and let us start again.
Yes. Okay. So we start from here, and we try to set up now a very standard perturbation theory. So let me start from my green function, g of z. So you know that if I treat my hopping as a perturbation, I have this relation. These are now operators. And then what I do when I do perturbation theory is I iterate this relation, and let me take directly matrix elements with respect to the local basis, which is the eigenbasis of G0. So I will have that my function matrix element between two sites A and B. So there will be a contribution from the first G0 only if the sites are the same, of course. So I will have delta AB Z minus the local energy. Then to first order in V, I assume, I have a contribution only if A and B are nearest neighbors, so that they are related by one hopping V, and then I have two energies. Then in the next order, of course, I have intermediate sites, which I can summon. So I will have VAC, VCB, epsilon A, Z minus epsilon C, Z minus epsilon B, and so on and so forth. So you see that here, if you work in the position basis, the diagrammatic is super simple. And think of this being simply a sum over paths. So you have your sites A and B, and what you do is you sum over all possible paths. So I should use a color, but I think you don't see it online. So you have all possible paths in the lattice which connect these sites A and B, and each step in the path contributes with a factor of V over an energy difference. So this G, A, and B, I have 1 over Z minus epsilon A, and then I rewrite it as, indeed, the sum over all paths P, which belongs to the sets which connect my sites A and B. And then the weight of the path is just given by a product over all sides. So from 1 to the length of the path, of ratios of V over energy differences. So now S is one particular site along the path, and S goes from S1 up to Sn, which is the length of the path, and then you see that I have these ratios, and this is what is called the locator, because it's like a propagator in locator. Okay, you don't see this. So it's the same idea as doing perturbation theorem in momentum. There you have propagators. Here you are doing it in position space, so you have things that you call locators. And this is called locator expansion in general. Okay, so this is for the green function. Now you can do the same thing, sorry, for the self-energy, local self-energy, where you have to sum, in this case, over loops around a particular site A. So this will be sum over the loops around A, and this for the way in which the self-energy is defined. Here you have to include only those loops which start at A, end up in A, but never go back to the site A along the way. So A is touched only at the beginning and at the end of your process. And you have the same type of expansion. So this is now sum over the length of your loop of V sk plus 1, Z minus energy at the site k plus 1, times an extra factor of V, which is corresponding to the last step. So Sn back to the site. So far, yes. I mean, as long as you have, now I'm going to sum over self-avoiding loops in a minute, but so far, as long as you don't go back to A, you can do loops around, you can go back and forth around particular sites, which are not A. But this is a good observation, so we will see that this is a bit of a problem when you want to argue about convergence of this expansion. So you will have to introduce self-avoiding paths and self-avoiding loops and do some sort of intermediate resummation. For the moment, let me look at this expression. And now what I can say is that if I stop at any order in my perturbation theory and try to look at, I take the imaginary part order by order of my self-energy, and I try to look at the distribution over this order of this imaginary part, what I can show is that my picture at any order in perturbation theory is precisely this one. So you can do it at first order. So at first order, this will be just the sum over all sites B, which are nearest neighbors of A. So let me denote it like this. B is the nearest neighbor of A. And then, okay, I take directly the imaginary part of this. I will have a factor of V squared, so forget the indices for the moment. And then I have, if Z is, as usual, E plus I eta, I will have the local energy square plus eta square times an eta at the numerator. And what I do is now I look at this sum and I average over this random local field. And as I said, you always get something which looks like this. And this is why, so why is it so? Well, because this is, as usual, your Lorentzian of width eta. And you're targeting here one particular value of energy. So you will have contribution only whenever you have a realization such that the corresponding local energy there is as close to epsilon as at least this value of eta. And if the distribution of these local energies is somehow continuous, the probability to be within, if you want, E and E plus eta is of order eta. And based on this reasoning, so this is a bit sketchy, but this is why you find that somehow most of your probability distribution is peaked at eta, and then the probability to get much larger values actually decays very fast. So order by order in your expansion, it looks as if the system is always is always localizing. And in fact, this makes sense with respect to what we said with this simple two-side system. So you know that whenever you have delocalization, of course, your perturbation theory in position space has to break down. And so you should see this in some divergence of the type of path expansions which I am writing in here. And so this is, let's say, the starting point of Anderson's reasoning. So the idea is that if you want a sufficient condition for localization to occur, so to have this criterion satisfied, then a suitably defined perturbation theory should be convergent. So a sufficient condition for localization is that renormalized, or let's say, okay, let me write suitably resummed, and I will clarify what I mean. Converges. So to show localization, we just have to argue that with probability 1 over our disorder realization, these type of expansions are convergent. But things are not totally trivial, so why do I write suitably resummed? Well, this is related to something that I tried to sketch when discussing question 3. And it is the fact that if you have this system in an infinite lattice, actually you do have, even if you are localized, you do have local regions in your lattice where your perturbation theory breaks down because you have to hybridize locally your degrees of freedom. And this is related to the fact that even in the localized phase, you have resonances in your system between your local degrees of freedom. But they are local. And what you have to care about is whether they do or do not proliferate if you look at larger and larger length scales. However, even if you have such a local resonance, if you go back to this naive perturbative expansion, this will give rise to subsequences in this expansion which are divergent. But they do not signal the fact that you are delocalized. They just signal the fact that somewhere in your random lattice you have to do some non-local rearrangement of the degrees of freedom that you have in there. So how can you get rid of this? Well, you do some partial resummations of this sum over path, which take into account these local resonances. And the idea is as follows. So this will lead to restricting our sum only over self-avoiding loops or self-avoiding paths. So the idea is as follows. Let me give an example. So suppose that in my lattice, I have two sites which are locally resonant. And I take, so these are the sites A and B. And I call this the site D. Now, what happens is that if I restrict only to A and B, I have terms which are of the form of V over the energy differences, which are actually very large. And when I sum over all possible paths, I also include in there all the paths which can jump back and forth this site an arbitrary number of times. So I get these large factors multiplied by an arbitrarily high power in my series expansion. So for example, there will be terms in my sum where, so I come from site C, and then I go from, okay, let me change the notation to be consistent with what I wrote. So I come from site C and I reach site B, and this will come with a factor like this. And then I will have one path in which I do not go to site A and I go straight to site D, but then I will have a path in which I am in B and I go to site A and I go back to B and then I go forward. Then I have another path in which I do this loop twice, and so on and so forth. So in here you will have all possible powers. Of this contribution of a single loop. And then, of course, eventually you will stop looping around and you will go to the next site in the path. So the idea is that I take all of this expansion, which is formally divergent when I have a resonant, and I resum it directly. So if I do this, this is a geometric series, so I will have a term like 1 minus VBA, VAB, Z minus epsilon B. And combining these terms, I see that I can define a modified locator corresponding to this step. So I bring this V inside here. Let me do it without rewriting it. And I bring the energy difference in here. So this would be Z minus epsilon A, and this will cancel one of the energy denominators in here. Now, if you did the two-site exercise that I gave, you recognize that in the case of only two sites, that's it. So that is actually the local self-energy at the particular site A. So this matches with my expression for the green function as being given by the unperturbed energy shifted by the self-energy at the site that I'm looking at. But in a system with a larger number of sites, what I have to do is to so this will not be enough. I will still have a lot of paths, and for each of these paths, I have to do some sort of I have to introduce some sort of renormalized locator, so I have to do this partial summation over the loops which have arbitrary length around the particular site that I'm looking at. So if you do this systematically, then you see that you can rewrite your expansion over path into an expansion over self-avoiding path. So let me perhaps write it directly for the self-energy. So you now sum over loops which are self-avoiding around the site A, so which never go back to the same site. And you have a modified weight of this loop that goes as follows. So suppose that I label my sites. So this is A, and then I have site 1, site 2, site 3, and so on. And I go back to A. So the first locator that contributes to my pathway is given by my hopping from A to site 1. And then I have Z minus the energy at site 1 minus a modified local self-energy at site S1, which I obtain by summing overall self-avoiding loops around site S1, which never go back to the site A that I'm coming from. And this is the first step. Then I do the second step, and I will have V S1, S2, Z minus epsilon S2, minus a self-energy at the site S2, where I sum over all loops around S2, which never go back to themselves and also never touch both sites which I already encountered in my path, which are A and S1. And of course, you iterate this through the loop, and at the end, you will have V of Sn minus 1 Sn, Z minus energy at Sn, and minus self-energy at Sn without crossing any of the sites in the loop. And then you have the final factor of V, Sna. Okay. And the idea is that whatever local divergence in the original perturbation theory that you had due to some local resonance, you are resumming it, and you have, in principle, a non-perturbative contribution now that you would like to treat, and therefore you would like now to show that this new expansion over self-avoiding path with probability 1 is convergent whenever you have localization. Okay, now this is something that in general you don't know how to do. And you don't know how to do it because you see there are now a lot of correlations in your locators. So if you look at one particular site along your path, you have to remember where you are coming from, so what is the history, if you want, of your path, and this depends on random variables, which then gets correlated, or make all of these locators correlated with each other. So in general, this is estimating precisely what is the distribution of this sum is something which is very challenging. And so what we are going to do is to follow Anderson and also subsequent works, and we are going to make an approximation that, as you will see, makes things particularly easy. Okay, so first let me say how one would like to prove convergence of this expansion. So the idea would be you have this sum over all possible self-avoiding loops, and let me reorganize them according to their length. So I now sum over the length of the loop, which goes from 2 to infinity. And then I sum over all those loops around A which have length n of the corresponding weight, and I put this subscript n just to remember what is the length, so the number of terms in my product. And to prove convergence, actually, so the statement that is actually argued for in this paper goes as follows. So you now take Z, which goes to some real value. And what you want to show is that asymptotically, so you see you have a sum over all possible lengths of your loops. So you take all values of n which are larger than a given threshold capital N, and you ask that the sum over loops of that length is bounded by some exponential in n, little n. With some Z, so you basically want to show that there exists some Z smaller than 1, such that if you look at sufficiently high orders in your perturbation theory in V, essentially, you can bound asymptotically these sums with something which is exponentially decaying. And strictly speaking, you want this to hold only for n which is large enough. Okay, so we are going to show that this happens for this order sufficiently strong, but we are going to do this within an approximation, as I said.
But you want to show that this link is what?
1. Yes, sorry. Right. So I want to show that almost surely higher order terms in my expansion are exponentially suppressed. Okay, so the approximation that you do to show something like that is what is called the forward approximation. Which is some sort of mean, you can think of it as some sort of mean field-like approximation. So if you work out this by doing diagrammatics in the many-body case, this would be a bit like working at the tree level in your diagrammatic expansion. And in here, it simply means that I take all of these modified locators and I neglect these resummations, these corrections to my local energies, which give me correlations between the different locators. And in doing this, so why is this called forward approximation? Well, because remember that this accounts for all processes where you go back you bunch back and forth around a given site. So if you neglect all of those processes, you will indeed end up by considering only processes where your path always moves forwards. It never goes back to a previously visited site. So it does loops which are indeed self-avoiding, but with the original locators. And therefore, you call it forward, this subsequent of your original perturbation theory. But the reasoning is, in some sense, self-consistent. So the subsequence that you are resumming is the one of forward path. And if you show that this kind of converges asymptotically, then you know that this corresponds essentially to the subsequent that you are putting into this self-energy themselves, and so this will also be asymptotically convergent. So the reasoning that you're making is a bit self-consistent in the sense that you assume that at least at large values in my perturbation theory, this decays sufficiently fast, and then if this is the case, I neglect this. I assume that the subsequence that remains decays sufficiently fast, and then I say that my assumption was self-consistent. Okay, but for the moment, okay, just think of this as an approximation which helps when doing the calculation. And so now things are pretty easy and we can estimate what is this distribution. So let me define as a n at a given energy E as just the sum, so the sum that I wrote before, only over the loops of length n. And let me, so now the length of the loop is given by little n. And then I have an extra factor of v. So now I'm setting all the VAB equal to v. And what I will do is also, I will choose one particular energy. So in analogy with what we discussed for MBL, I put myself in the middle of the energy band. Because in general, states at zero energy are the first one to delocalize. So I want to estimate for which value of disorder I have that the full spectrum is localized. So to get this, it's good to focus on the ones which are more prone to delocalization. And I will take, just to do the calculation, I will take my local energies to be extracted from, let's say, a uniform distribution of width delta. Okay, so if I plug this into here, what I can do is this is equal to 0. Well, I absorb the minus because the distribution of this epsilon is symmetric. And I rescale by the typical disorder size. So I will have that this is for E equal to 0. The object that I want to control is the sum over all loops. Now I drop this, this notation of V to the power n plus 1. Then at the denominator, I factor out delta over 2 to the power n, and then I am left with 1 over some energy which is normalized to 1. So the distribution is now uniform between 1/2 and minus 1/2. No, minus 1 and 1, actually. Okay. Now let me focus on one particular, and I forgot the product, sorry. This is a product over k of 1 over epsilon pi of k. So now I focus on one particular loop, on one particular path, and I compute its distribution. So this is a product of random variables. So my, let's say I call xn my product of 1 over epsilon prime of k. And since I just want to estimate what is the probability of its amplitude, let me factor out any fluctuations of the sign. And I compute what is the distribution of this x. So this is quite easy to get. So I will write it down, and then I will tell you how you get it. So the distribution of my x will depend, of course, on n. It is of the form log of x to the n minus 1, n minus 1 factorial. And then I have an important factor of 1 over x squared. Now, how do you get this? So this is just an exercise, if you want. The idea is that you want a distribution of a product, so it is always convenient to to make a change of variable, take the log of this product. Because in this case, this will be the sum of, from k going from 1 to n, of some quantities which are independent with each other, that I call y. That is simply minus the log of epsilon prime. Then you compute what is the distribution of y, and you will find that this is simply an exponential. So the p of y is an exponential distribution. And what you do is, since you want to estimate the probability of the sum, it is always convenient to go to compute the characteristic function. So the expectation value of e to the s times your variable. And the reason is that this is a sum of independent variables, so you will just have the characteristic function of 1 of your y's to the power of the number of terms in your sum, which is equal to n. So if you do the calculation for this exponential, you find that this is 1 over s plus 1 to the power n. And then what you have to do to get back to the distribution is to do the anti-Laplace transform. And this will be contributed by, you see, you have a pole which is not simple, but you know how to compute this integral in the complex plane, and this will give rise to these factors depending on n, and then you go back from y to x, and you get this distribution of the product. So, okay, this is just calculus, but the important point is this factoring here, because this tells you that the distribution of your product has tails. So it does not decay, for example, exponentially fast, but it decays with some fat tails. Cauchy-like. And therefore, when you want to sum over many of these products, you cannot use central limit theorem in here because you have a distribution that doesn't have a finite second moment. So what this means is that if I look at this sum over many terms, when n is large, this sum will not scale like the square root of the number of terms times the typical value of this product, but it will actually scale like the maximal value among all those that you are summing on. So when n is large, your Sn will be scaling like the maximum overall loops, self-avoiding, of, well, you have your factor, so let me just simply write it, of the amplitudes of the loop itself. And therefore, if I take the absolute value here, what I have to do is simply to estimate how does the maximum value over all my loops scale when I take n large enough in absolute value. And now the point is that when you have distributions which are tailed and you sample them over many realizations, so you have many loops that you're looking at, you will find that the maximum over all these loops will be essentially quite larger and quite far away with respect to the typical value of this product in here. So the typical value is something that you can estimate once you have the distribution of x. So what is the omega or x typical? No, okay. Omega n loop typical value. So this you get as E, you compute the average of the log of this loop, and then you exponentiate it, so this will give you the typical value. And if you do this, you will find that this is, I'll give you the value. This goes like 2 VE delta n times the extra factor of V. So you see, at the level of a typical value of one path, if I choose delta large enough so that this factor is very small, I have an exponential suppression, and I would be tempted to think that, okay, the problem is solved. It is enough that I make this quantity in here sufficiently small, so smaller than 1. And I know that typically each contribution to my sum is exponentially bounded when n is large enough. So this is for large n, of course. No, here not. But. And therefore, I am in business. But actually, the problem is more complicated precisely because this sum is not scaling as the typical value, but it is scaling as the maximum. And when you maximize over many sampling, you're actually dominated by rare values of this path weight, which can be much, much larger than the typical value. And they can become of order 1. And in this way, you spoil the convergence of your loop expansion over loops. So what you have to do is to estimate when this is not the case. And this is the following. So to estimate this, the first information that you need is how many loops you are optimizing over. So this, I will write it here. So this is one useful information. And the second one is you want to know what is the scaling of the number of these self-avoiding loops with the length of the loop itself. So I will call this n of n. And you find very precise results in the literature. I put them in the references. But for us, it is just important to know that this is a scaling which is exponential in n, as I think you expect. And the coefficient is something that depends on the particular lattice that you're looking at. It depends on the dimensionality, so I will call it log of k d, and then you have subleading orders in n. This is a constant that you can determine depending on the lattice that you're looking at. And so now I can compute what is the probability that I call Pn, which is the probability that the sum over all contributions of order n to my self-energy is bounded by some z to the power n. Now this sum, when n is large, I can roughly replace it with the maximum over all my loops of size n of the amplitude of the loop. Now, here, in principle, the weights of all your loops are not independent because you may hit the same sites in different loops, but you make the approximation which actually works not too bad, in particular in higher dimension, that you can neglect the correlations between your different loops at n large, so you approximate them as roughly independent. And you say that the probability of the maximum, so to have the maximum which is bounded by something, it means that all the loops have to be bounded by that something. So this is, if you use independence, roughly the probability that one loop is bounded by z to the n to the power of the number of terms you're maximizing over, which is this n of n that I introduced before. Okay, now I exponentiate it. So here I have a log of the probability that this is smaller than something is 1 minus the probability that the same term is larger than z to the n. And now this is good because if I choose z which is close to 1, and if I assume that my parameters are such that this ratio here is instead much smaller than 1, then in here what I have is essentially a large deviation probability. So I'm asking what is the probability that the amplitude of my loop is much larger than what its typical value. And therefore this, you can compute it explicitly, of course, but this is a large deviation in the sense that this probability will be exponentially small in the length of the loop. And actually, perhaps I will write it down. So this, if you plug in the expression for the probability P of, so this will be, you have to integrate. Now remember that I rescaled my loop amplitude to get x, so here I will have the rescaling factor which appears. So I have to compute this, I plug in the expression that I gave before, and I find that this will be of the order of e to the n. Log of 2ve over delta, log of delta z over 2v, and then I have subleading corrections in n. Okay, and if I have this and I combine it with this, I am basically done, because now continuing in here, what I can say is that this Pn is roughly equal to e to the number of loops, which was little n log of kd times plus corrections. And then this log of 1 minus something which is exponentially small, I put a minus in front, and I approximate it with the quantity which is small. And so this was, sorry, I forgot an exponential here. So this is e to the n log of kd times this exponentially small probability, which I can include into the log. So I have 2VE delta log of delta z over 2V plus correction in n. And now I'm done, because this is basically the probability that I can put an exponential bound to my self-energy at order n in this resummed perturbation theory. And I see that this probability converges to 1, provided that the quantity that I have in here is negative, so that e to the n times the log of, so a quantity which is negative goes to 0, and e to the 0 is of order 1. So the criterion that I get out of this simple calculation is that this kd times 2VE over delta times this log, delta z over 2V, this has to be bounded by 1. Now, z was arbitrary, but of course, I only have the condition that it is smaller than 1, so let me take the threshold value and put it equal to 1, and in this way I optimize over the criterion, and this is precisely Anderson's estimate for the localization boundary, or for the localization-delocalization transition. And you see that you use really the fact that rare effects matter when you do this estimate, because if you just accounted for the typical value of a path, you would have roughly this. But then you have a log corrections, which takes into account the fact that you can have, since you are sampling over many, many paths, you have rare events which show up in your sum. And this is very glassy, if you want. So you have, it is very similar to simple glassy models in which you have freezing or condensation. So you have, for example, partition function, which are sums of many terms. And actually, you see that this condensates, and the number of terms which matter is not exponentially large, but it is actually of order 1 in your dimensionality. So here, it's something similar. So you have all these possible paths which can bring you from one site to another one, and most of them will be exponentially bounded. But then when you approach the transition, since you have so many, exponentially many, you will eventually find one path which is of order 1, and this is enough to restore transport in your system and give you essentially delocalization. And this comes in precisely because of this battle of exponentials between rare events and large number of trials that you can make. Okay, so now this, I think, maybe roughly concludes what I wanted to say on this. Okay, so you may wonder what is the effect of the approximation that we did of neglecting self-energies, and actually what you can show is that if you just want to argue for the existence of localization, this is fine. So you are essentially underestimating the region of parameters where you are localizing. So the idea is that if you restore your self-energy corrections, you make your localization stronger, and you get actually a value of disorder for localization which is smaller than what this estimate gives you. And this was shown already by Anderson himself. And this is why he called this forward approximation an upper limit approximation, in the sense that it gives you an upper bound on the critical disorder that you need. And then there are, of course, connections to glassiness that I kind of hinted at. And I just wanted to conclude going back to the many-body case. So I say that if you think at the problem in terms of conserved quantities, then you map your problem of determining the amplitudes of your operator expansion essentially to a problem which is similar to this. So as I said, it's much more complicated because even if you do the forward approximation here, your locators are still correlated, so they know about the fact that you are many-body, and this shows up in non-trivial correlations. Your lattice is more complicated, but you argue more or less in a very similar way, and you can show that there is a finite region of parameter. In that case, the role of the hopping here is played by the interaction. So if the interaction is sufficiently small, then you can show that these amplitudes are exponentially bounded. And so this is one way to think about MBL in these terms. And the other way is to do more directly computations that have to do with computing diagrammatics for the self-energy, which is precisely what we did in here. And this is what you find in these important papers. This is 2005 or 2006. So what they did is to write down the self-energy for the many-body problem, and then they did an approximation which is the imaginary self-consistent Born approximation, but it is very close conceptually to the forward approximation discussed in here. They do diagrammatics, and they argue that this sum over diagrams converges. Now, in our case, the diagrams were very simple, so you have just one step in a path, which contributed with a factor of V over an energy difference, if this is the site A. In the many-body case, what plays the roles, again, of your hopping is actually the interaction. So your unperturbed Hamiltonian is the single particle Hamiltonian, and the perturbation is your interaction. So the type of diagrams that you have are usual scattering diagrams that you combine, and what you have to show is that the sum over all diagrams at a given order of perturbation theory, if you go to high enough order with probability 1 is bounded, and it gives you an expansion which converges. Okay, so maybe it's, I think, time to stop. I can perhaps, to conclude on this many-body case, add the very last comment, which is that if you go back to the Anderson model, so now we reasoned in infinite dimension, but there is a limit where the equation for the self-energy which I wrote actually closes and becomes a self-consistent equation for the probability distribution, and that is the Bethe lattice. So on the Bethe lattice, you can actually solve the Anderson problem. You can do it both within the forward approximation, but you also have an exact solution when the connectivity of the lattice diverges. And you will see that the exact solution gives you a critical condition that is very similar to this, except for some numerical factors here, which are actually different. So you have to replace this E with a factor of 2, I think. But somehow, in there, you can reason a little bit different. You can write down self-consistent equation for the full probability distribution of your self-energy, and you can work directly in terms of distribution. And this is very useful because your many-body case, you can often think at it as being approximately like a single particle problem in a lattice which looks like a Bethe lattice, in the sense that the number of configurations of your Hilbert space grows exponentially, like precisely in the Bethe lattice. And so having good control of this particular case, I think it's very useful if you think in terms of many-body localization as well. Okay, so thanks.
So there will be the discussion session in 5 minutes or 10 minutes, but if there is somebody who needs some short question, just please go ahead. Yes, please, Johan.
So I'm just wondering,
sorry.
could you comment on I'm wondering if you could comment on the basically the localization delocalization position about the dimensionality, because is it easier? It seems to me that this k of d probably increase when you have higher dimension. So
Yes.
does it mean that it's harder to localize in a higher dimension? Yes,
because naively the number of paths, the number of decay channels gets bigger, and so it gets higher. But the question is interesting actually, because at the level of this reasoning, apart from d equal 1, where you don't have this exponential number of paths, but for example in d equal 2, this would still give you a transition, this approximate reasoning, but we know that in d equal 2 actually you do not have a transition to delocalization and your system is still localized. But the mechanism there is a bit different, I would say. It has to do with this destructive interference of one path and the time reversal version of the path, and you have to go beyond this. And I comment on this. I give reference on this in the file, supplementary file. So there are kind of renormalization group arguments that date back to the 80s that are able to recover the fact that you have a transition above 3 dimension, but the lower critical dimension, if you want, is 2.
Okay, thank you.
But you still have a transition in the beta lattice, which maybe is surprising.
Other questions?
What is the beta lattice?
Yes, sorry. Good point. So it's a lattice, it's a tree-like lattice, which looks like this. So I have, it's a lattice with no loops, if you want. So each side have a fixed number of neighbors, which is called the connectivity. So in this case, the connectivity is 3. And you go on branching forever, and you see that you have no loops, in the sense that if I move away from this site, there is no way that I can come back, apart from retracing the path that I did. This is the beta lattice. And the reason why things get easier, and this is very general when you think about cavity methods in statistical physics, so you have recursive equation which usually close in this type of lattices. So if you think about the self-energy, so just to sketch the idea. So let me consider now not a beta lattice, but a real tree where I have a special site, which is the origin. And I call this A, and I want the self-energy at the site A. And I say that this, I could write it, let's say, as there is a V square, perhaps in here. And then I have Z minus epsilon A. And I should sum over all the sites which are connected to the site A, a local self-energy. So if this is, OK. So I should get a different notation. So this is the so-called, is this sum over all loops that are never self-tracing. So in here, I will have an analogous sum where, let's say, I sum over the sites B, which are the zones of the site A in my lattice. And then I have to sum over all loops around site B that never go back to the site A. But never going back to the site A is like equivalent to cutting this edging here. And what I'm left with is a subtree that in the thermodynamic limit is stochastically equivalent to my whole tree. So here I will have a cavity self-energy at the site B. And when I think about distributions of these objects when the tree is infinite, this guy here and this guy here essentially have the same distribution. So I can write down a self-consistent equation for my probability distribution, and I can directly attack my problem looking at the distribution of this quantity without going through this perturbation theory.
Also questions?
So the reason why this lower critical dimension of 2 does not hold for the beta lattice is that in practice it's not a two-dimensional system. Is it something like that? The effective dimensionality of this lattice is different?
You ask? No, so for the beta lattice, you have something similar. Here you would just get the branching number of the lattice. The point is that this is obtained within this forward approximation. And this forward approximation, so neglecting this, is not a good approximation even when you take a lattice like this, and even when you go to a number of neighbors which goes to infinity. So you may naively think that this forward approximation is some sort of mean field approximation that should be correct in a beta lattice with infinite connectivity or in the limit of infinite connectivity, but this is not true. So to get the right pre-factor of the log, you really have to always keep these self-energy corrections.
Okay. Thank you.
But the rest of the terms are correct.
Further questions?
If I look at this calculation, it seems, very quantum, no? Because you have propagator and, so what could be a classical analog of this phenomena? I mean, you already had this question, but I can ask it again now, since I can see the derivation of this bound.
No, I agree in the sense that...
You said that there was classical localization, so in which sense? So what can I take from here to classical waves?
Yes, so I think the picture that comes out from classical waves would be more appropriate if you think about lower dimension. And what I'm saying in here is more what captures what's going on if you are in higher dimension. But you may think about, so somehow I'm using the fact that, yes, this perturbative expansion, of course, is quantum in nature. You would not have something similar if you solve, in principle, classical systems, but you can think about classical systems where you have enough heterogeneities in, it's like when you do Poincaré expansions and you have also these energy denominators in classical systems, and you have to come up with a mechanism that gives you an energy scale for this denominator which doesn't go to 0 in your thermodynamic limit. And here it's disorder, because when you have this localization, you have an effective local energy scales, which is not the spectral gap. It is actually governed by this delta. So if I focus in a finite region of space, my eigenstates in there will be separated by delta, not by the spectral gap. And this helps in controlling the denominator. Whether you can really find a classical model when a similar mechanism works with this formalism, I don't know. But to really answer, I think, when I think about localization of classical waves like electromagnetic waves and so on, I always think that that is the picture which is more appropriate in lower dimension, where all of these approximations that I did are actually very wrong. I mean, even neglecting correlations between paths in low dimension is wrong. In 2D, they will overlap a lot. In high D, they will overlap much less, and so you're fine.
Yeah. Sorry, very stupid questions. But at some point you said E equals 0.
Yes.
So, I mean, if you were not doing that, where would E enter in the final formula?
Yes. So you have to compute again the distribution of your product for so you have these products going from 1 to n of V over E minus your random variable. So the distribution of this object will, of course, show a dependence on E, and therefore your criterion here will show a dependence on E, and usually this will give rise to what people call mobility edges. So the critical point, so let me put V here, and this is the spectrum, so this is V over delta. So if I'm looking at zero energy, that gives me a given estimate so this will be localized and outside will be delocalized, and then you typically have some mobility, some dependence on energy of this critical coupling.
Maybe we should not make, oh, sorry. Maybe we should not make any break and just go on with the discussion sessions since we are already doing it. So I would like to ask also to all the participants, online participants, if there are questions to Professor Cooper. Or to Professor Ross as well, to anybody.
Yeah, a question to Valentina Rose about the conservation laws. I think it's very anti-intuitive because I think you encounter a large number, an infinite number of conserved quantity in normally integrable system, but I think for many body localization, it's highly disordered or chaotic. But so for me, it's very anti-intuitive. You also have this large number of conserved quantity also appear in this kind of system. So
no, you're totally right. I think it's quite different. I mean, in clean integrable system, you have algebra behind. And so you have a structure that also allows you to you have also recipes to build them which rely on this algebra. And here, no, and you see this because the I alpha that you have, they explicitly depend on the disorder realization. So you have that statistically, you have this operator for every disorder realization, but if I give you one specific Hamiltonian, every time you have to come up with a recipe to find the particular conserved quantities for that given Hamiltonian, and they will be highly dependent on the disorder. But if you think at this, so one way to, I think the easiest way to think at this is that is really in terms of perturbation theory. So you have Hamiltonians which are of the form, let me think about a spin chain. So you have your randomness which couple with one particular basis. I choose sigma z, and then you have your hopping, so sigma plus I, sigma minus I plus 1. Plus you may have Ising interactions. And you somehow want to do perturbation theory with this, on this term as compared to this term. And the fact that this disorder is strong is telling you that basically this term wins, and it wins really in the sense that each single eigenstate of your Hamiltonian is not too far from a simultaneous eigenstate of this sigma z. And then you see that actually the conserved quantities, so it's surprising at the beginning that you have them because you have no algebraic relation behind, but this is just telling you that this disorder is so strong that it selects a special basis, and the full eigenstates of your Hamiltonian have a huge overlap with the ones in this special basis. So from this perspective, I think this is more easy to accept.
Further questions?
Yes. Can you hear me?
Yes, please.
Yes. I have a question which is kind of broad regarding not only MBL but also other phases. And
What is the speaker?
oh, should I turn my camera
Sorry, could you
on?
repeat the question, please?
Yes. Should I turn my camera on as well? Do you have?
Okay, wait. Let me do this, and then I think we will see you.
Yes,
Yes.
it's a good idea.
Okay. So first of all, thank you for these lectures and this very extensive description of MBL.
Thanks.
And so one first point is that you have given us several ways to characterize MBL, but my impression is that in the end, let's say from an experimental point of view, the most simple way to characterize it would be still from the point of view of transport.
Yes, but it also depends on where you want to check that. I mean, I have to stress once more that the statement that you have no transport is for a system which is isolated. So of course you may think, okay, the easiest thing to do is I take a magnet or I take a piece of metal and I want to check that this is an insulator if I put disorder strong enough. But in real matter, you usually have a lot of couplings with phonons, for example, in materials, and that would be like coupling to the bath. So all of this would become much weaker because of this coupling. So you have to work with materials such that the couplings with this bath-like degrees of freedom with continuous spectrum is very weak, which allows you at least to probe over some timescales the fact that the system is isolated. And of course, cold atom is one example. So it's true that experimentally one would naturally think about transport and conductivity, but one has to keep in mind that it is the framework where you are discussing this requires you not to couple to other degrees of freedom. But when Anderson started, I mean, he was looking at data from the Bell Labs, which were about thermal conductivity in magnets. So actually, I mean, the starting point is precisely what you say.
Okay. And this leads me to a kind of more general question, which is, so if I have a system which has both disorder and interactions, so I understand that we can have a kind of MBL phase which is localized and insulating from the point of view of transport. But we could also have a phase which is more of the kind of a not insulator, let's say, which is still insulating.
Yes, but here you are really at excited energies. So that band insulators, so you reason in terms of, let's say, lower excitations of your spectrum. So here you have an extensive energy and a highly excited many-body state. So it's a bit different. It's really more thermodynamics than ground state, I would say. So thermodynamics, I mean, the thermodynamic setting at higher temperature than being close to zero.
Okay. So if I were to think about what happens to MBL at higher temperatures, like where should I be looking at then?
I didn't hear you, sorry.
Sorry. So you're saying basically that Can you not hear me?
Yes, kind of. But it's not your problem. I think it's the speaker here that is not great. I mean, la cassa. But go on.
Okay. I was just trying to understand, let's say, if there is a... Because in my mind, if I have a system with strong interactions and no disorder, let's say, I can still have a ground state, which is a kind of a Mott insulator ground state.
Yes.
And then, so let's say if I have disorder and very weak interactions, I would imagine to have an MBL localized state.
Yes, so so if yes, you can have phase diagrams, dynamical phase diagrams that are reentrant. I think this is what you are thinking about, that you have a non-monotonic.
Kind of.
Yes,
My general question was how could I distinguish between these two situations, since in the end they are both insulating.
So I think I would, I mean, physically what makes all of this surprising and the way you would distinguish between the two is the fact that in one case you're really, let's say, at low temperature, close to the ground state, and then you can have physics which is the one of an insulator, but okay, to some extent you understand this, and it is not too surprising. Whereas in here, I mean, you really have a state which is really highly excited. So you have a lot of these particles which are free to scatter. The scattering may be weak, but you have a lot of those excitations, extensively many. So, or they give rise to an energy which is extensively above the ground state. And you still see that despite all of this energy that you have in the system, you are not able to somehow spread it and transport it and have the phenomenology of thermalization that you would expect. So the setting is, I mean, being close to the ground state or being at highly excited state, I think makes a difference, at least conceptually.
Okay. So basically you're saying that one way to distinguish them would be what happens to the conductivity when we raise the temperature, in a sense.
Yes, exactly. So in here you would have a mobility edge, which separates parameters where you do not have transport to parameters where you have transport, which is extensive in the energy. In the other case, it is intensive in the energy.
Okay. I will have, of course, to think about it a bit more, but thank you very much.
Thanks for the question.
Other questions?
Why one should be interested in the study of this phenomenon on beta lattice? There is a...
In the beta lattice,
yes,
say?
there is
okay.
an experimental reason, or is just a playground where calculations are easier?
No, so the beta lattice is not realistic, of course. So people use
exactly.
it in StatPhys because it allows to close equations and so on. But I mean, the fact that the many-body case. So let me go back to this idea of coefficient in your expansion. So this quantity that appeared when constructing integrals of motion. So this is a problem which is many-body, and you're interested in this. It is a realistic setting with the caveats of no bath and all that. And somehow when you study this type of Anderson problem, what you have to understand is, so you will have equations which relate your amplitude at different sites. And you have to understand how are the sites organized. So what is the structure of the lattice over which you want to show localization.
Dovresti rimettere la blackboard.
And to do this, you have to look at this equation. So this equation comes from imposing a commutator equal to 0. Then you project on a basis of operators to reduce this to an equation of amplitudes. And there are terms which relate amplitude at different sites in this effective lattice. And these terms depend on the strength of the interaction. And if you look at the structure and you work out the type of lattice that you have, you see that you have something which is a bit like this. So the root of your lattice is the site alpha alpha, around which you are perturbing, if you want. So this I alpha was an expansion, was an alpha plus corrections coming from the interaction. So you have a special site, which is the one around which you are perturbing, and then all the other sites are connecting in this way, and this link means that the amplitude at a site is related in the equation to the amplitude of at the other site. And you see that you can indeed organize your sites in this effective operator lattice in 2 generations. And the number of terms of sites in each generation scales exponentially with the generation, exactly as a beta lattice. This is not exactly a beta lattice because here you do have loops, and you have to pay attention about controlling the loops. You have higher correlations, but it is not too far from a beta lattice. So from this many-body perspective, it is interesting to have a good understanding of this. But if you just think about single particle localization, no. Yes.
Other questions? This is a problem. Ma ci vedo o no? Sorry, a few seconds of patience.
Yeah, now it's
Okay. So any other questions? Also on other lectures? Any question for Professor Cooper? If not, I would like to thank all the participants for their patience, also to attend these lectures online, which is, of course, not easy. I would like to excuse us for a few technical issues, and I would like to thank also all lecturers for excellent lectures, and also, again, for coping with all the difficulties in lecturing at a distance. And I would like also to say that I really hope that the next session of Statistical Field Theory School will be in presence next year. It will be the first decade of the school. And so it will be a good occasion to be all in presence here. Thank you very much.
Good.